This lesson is about probability. We're going to work on looking at independent events and mutually exclusive events and the probability. So our objective is being able to find the probability of independent events and mutually exclusive events. So let's start with probability. Just as a reminder, probability is where you measure success. What does a successful event look like? And what is it over the total? Because if you put success over the total, you'll get a fraction between 0 and 1, possibly equal to 0, possibly equal to 1, but somewhere in between those two. We'll list it as a decimal or a fraction between 0 and 1 inclusive. So 0 and 1 can be possible. So what does it mean to be independent? Independent is when you have two different things that you're measuring, two different events, that the occurrence of one does not impact the probability of the other. So the occurrence of one event does not impact the probability of the other event. So there are two things that don't influence each other's probabilities. So if that's true, A and B are independent events. If the probability of A and B equals the probability of A times the probability of B. So what this means, remember what this arrow means, is that if A and B are independent events, then this formula is true. And if this formula is true, the other direction, if this is true, then this is true. So it's an if-then that goes both ways. We sometimes call that if and only if. So the key word here is if you have the word and, then you're going to, and they're independent, then you're going to multiply the two probabilities together. All right, let's take a look at some different examples. Now, just a probability event, just one event. What's the probability of getting heads? That's equal to 1 success out of 2. One side of the coin is a heads, and so that's your success. We'll come down and we'll look at that. We'll look at that combined with other probabilities. Talking about cards, what about the probability of red? Now that's just one event, but how many red cards are there in a deck? Well, there's, if you recall, there's 26 red cards out of 52 cards in a deck. Now what we want to make sure that you recognize, if you don't remember this, for cards, there are 52 cards in a deck. And if you don't recall the idea of the different suits of it, there are 4 suits. Now what a suit is, remember, that's where you have hearts, diamonds, those are your red cards. Okay, so that's why there's 26 of them. And then there's also spades. And then there's clubs. So red cards, there's half of the cards are red. So you don't have to do 26 out of 52. You could just know that 1 out of the 2 types of cards. There's red and black, so 1 is success out of 2 possibilities. So what about picking, if you go on and pick a card out of a deck of cards. So you just at random, you pick a random card out. What's the probability of getting a black 5? Well, there are 2 suits that are black, spades and clubs. There are a 5 in each of those suits, so there's 2 successful possibilities there out of the 52, which will reduce down to 1 out of 26 as your probability. So now let's do an activity. Let's flip a coin, so we have this probability, and pull a card at random out of a deck. What's the probability if you do that at random? You get a heads for flipping the coin and a black 5 for pulling the card. Well, that would be taking, since these are independent events, flipping a coin here does not influence pulling a card out of the deck, so they're independent events. They don't influence the probability of each other. So the probability of a heads is a 1/2. The probability of a black 5 is 1 out of 26, and we multiply the two probabilities and we get 1 out of 52 for our fraction. All right, how about this next one here? Let's do a tails and an ace if we're flipping a coin and pulling a card. So a tails is still 1 success out of 2. Now, these are independent events, but pulling an ace, there's an ace in each one of these 4 suits. So there's 4 aces in the deck. So you've got 4 cards out of the 52. Now we can reduce that, and it makes sense to think of it a different way, that the ace is one type of card out of 13. If you know in each suit there's 13 cards, so an ace is 1 out of them, so we're going to pull 1 out of the 13 different cards is what 4 out of 52 reduces down to. That gives me 1 out of 26 as a probability for getting a tails and an ace in this, doing this with these 2 events. All right, let's look at now dice, and let's look at marbles in a bag, another type of problem that we'll have. So in dealing with dice, remember you roll a dice, the dice has 6 faces, it has 6 numbers on it. So probability of getting an even, there are 3 even numbers and 3 odd numbers on a dice. So it's 3 out of 6 possibilities. That gives me 1/2 is the probability of getting an even when I roll a dice. Now if I roll 2 dice, all right, now if I roll 2 dice, that's 2 different events. This dice does not impact this dice. They're independent events because the probability of one dice does not influence or impact the probability of the other. So what's the probability of getting a 4 and an even? So on this one, to get a 4, that's 1 out of 6. Even is 3 out of 6, but let's just make that, let's reduce it down to 1/2, down to our reduced version, so 1/2. So what's the probability of giving a 4 on one dice and an even on the other, so 2 different events? I get 1 out of 12 for that probability. All right, let's talk about marbles in a bag. So this is, you got a bag of marbles, and you were going to be reaching in and pulling marbles out at random. Now let's say this bag contains 4 green marbles, 3 white marbles, 10 blue marbles, and 3 red marbles. That's a total, when you add up all those marbles, we've got a total of 20 marbles. Now that's important because this is when we do probability. Probability is where we measure something over the total. So what's the probability of getting a green marble? Well, to get a green marble, we're going to have 4 successes out of our 20 possibilities. 4 out of 20 reduces down to 1 out of 5 as our probability. All right, now what if we want to pull a marble, replace it, so put it back into the bag and pull another marble. Now notice those are independent events because if I pull out a marble and I put it back, the next one is totally random with the same probability for all the different marbles. So what's the probability of getting a white on the first event and getting a blue on the second? Well, getting white is 3 out of 20. We're going to multiply that by getting a blue, which is 10 out of 20. So it's going to be 30 over 400. Or we'll reduce, take out a 10 out of both of those, and you get 3 out of 40. Now, as you notice, it might be best if I reduce this down to 1/2. That might be easier to do your reducing at the end if you reduce the fractions before you start. So that's working on probability of independent events. Okay, so let's go ahead and do now mixing a couple of these different. Let's do cards from up above and a red marble. So let's say we want the probability of pulling, when I pull a card out of the deck, and a marble out of the bag of getting a diamond and a red marble out of these situations. Now, notice these are independent because the card deck and the marble bag don't influence the probability of each. So the probability of getting a diamond is one possibility out of 4 suits. So I could write that just as 1 out of 4. You could also write that as 13 diamonds, because there's 13 cards that are diamonds out of the 52, but that would just reduce down to the 1/4. We're going to multiply that by, and we've got red here, 3 red out of 20 total. So I'm going to multiply across and I get 3 out of 80 as my probability of these 2 independent events of getting a diamond and a red marble. All right, now let's go ahead and turn our attention to mutually exclusive. So this was independent, and you have independent events means you have 2 events that you're dealing with. On this now we're going to talk about, okay, when we look at outcomes, and we're going to just look at one event, but that sometimes there's overlap and sometimes not in what we're thinking about doing with this. So let's go ahead and talk about what that means. Mutually exclusive means that there's no overlapping outcomes. Okay, no overlapping outcomes. So these Venn diagrams help illustrate what we're talking about. So if I'm talking about something that I'm going to call success being these 2 things, notice that these do not overlap at all. So these are mutually exclusive. Whereas these 2 do have an overlap. This area in the middle here is the overlap, so these are not mutually exclusive. So for these, if we want to talk about getting, we're going to talk about getting a, maybe we're looking at pulling an event out, like we're talking about a red marble, we're talking about pulling out a marble. And let's say in those marbles we said, what about if success is measured as pulling out either red or green? So both of them can be success, but we're only doing one event of pulling a marble out of the bag. So it's 2 different things. There's no overlap between the red marbles and the green marbles, so they're mutually exclusive. So if A and B are mutually exclusive, then the probability of A or B is equal to the probability of A plus the probability of B. So on that last one, if we're talking about pulling out a marble, green or red, the probability of the green added to the probability of the red, it will be the one event that's success. Now, what if they're not mutually exclusive? If you look at something like this where there's some overlap, let's say that I'm rolling a die and I talk about the probability of getting a 4 or an even, those overlap. 4 is even. So when there's overlap there, you're counting this part twice in your probability. So what you have to do for probability of these, you have to go probability of A plus the probability of B minus the probability of the overlap. Okay, so that's where we have both of them occurring. Okay, so that's where you gotta be looking for where they overlap, and that's where we'll subtract. All right, so the key word here for using these, notice that we're using the word or here. For independent events, we used and. This is saying one event, pulling a marble out or rolling a dice, just one event, pulling a marble out, success being measured as 2 different things that don't have any overlap or do. We're gonna calculate those. All right, so let's give some examples here. What's the probability of a king or a red queen? Now, if I pull out a king, that's not taking any of the red queens away. So there's no overlap between those 2. So if success is measured as a king or a red queen, to figure out the probability, what you're gonna do is figure out what the probability of a king is. there's 4 kings out of the 52. And we're gonna go ahead and add to it the probability of the red queen. The red queen, there's 2 red queens, diamonds and hearts. So I'm gonna have 2 out of my 52. Add those 2 together and you get 6 out of 52, which we can take a 2 out of each of those and I get 3 out of my, let's see, that'd be 26. So 3 out of 26 is my probability for this. This is success, but one event, pulling one card out and getting either this or that. I get to combine the 2 probabilities. Now, what about the probability of rolling a 3 or a 4? Well, again, rolling a 3 does not overlap at all with rolling a 4. They're 2 distinct outcomes there. So rolling a 3 is 1 out of 6. Rolling a dice and getting a 4 is 1 out of 6. So the probability of getting a 3 or a 4 is 2 out of 6, which reduces down to 1 out of 3, which makes sense. There's 2 successes, possibilities, out of 6 possible outcomes. Okay, now what happens if, let me add one more on here. So what if we wanted to do the probability, if we wanted to do one that wasn't mutually exclusive? So let's say, what's the probability of getting, when I roll a dice, I'm sorry, let's do cards, of getting a king or a red card. Okay, so not red queen, but just a king or a red. Now, what we have to recognize is that there are 2 red kings in the deck. So if we're doing this, we've got to make sure that we see the overlap, because the probability of this will be probability of a king. We're going to add to it the probability of the red card, and we're going to subtract the probability of the overlap. So the probability of the king, again, there's 4 kings out of the 52 cards. We're going to add to it red card, there's 26 cards out of the 52. And then we've got to subtract the fact that we counted the red kings twice, here and there, so we've got to subtract it once. So we're going to subtract 2 red kings out of the 52. So it's going to give me a 28 out of 52. Taking out a 2 out of that, and we're going to have this be a 14 out of 26. I guess we can take another 2 out, so we'll have a 7 out of 13 for our final probability. So this is when they're not mutually exclusive. All right, let's do the complement of an event now. So we've done mutually exclusive, we've done an independent. Complement of the event is when you have everything, you want to do the probability of everything not in what you're, the occurrence that you're talking about. So everything not in the event would be the complement of it. So what would be the complement of hearts? Well, the complement of hearts would be the spades and diamonds and clubs. Everything else in the deck of cards besides the hearts would be counted in the complement. All right, so the probability of the complement of an event, how we can calculate this, often it's helpful to know that that 1 is the largest we can get. If we subtract off the probability of the event from 1, we'll get the probability of our complement. All right, so let's look at some examples here. What's the probability of not hearts? Well, not hearts would mean I'd have the probability, I'd have 1 minus the probability of hearts, which equals 1 minus, probability of hearts is 1 out of 4, because there's 4 of the different types of cards where we have all 4 cards. So 1 minus that would be 3 out of 4. Okay, so that would be the same as if we just said, okay, let's count spades, diamonds, and clubs. That's 3 out of the possible 4 for those. Now what about the complement of rolling an odd or a 4? Now notice those, if we do that, there's no overlap between odd and 4. The word or tells me I'm looking at, are they mutually exclusive? They are. So what's the probability, first of all, of an odd or 4? Well, I can go ahead and add those two probabilities. Odd would be 3 out of 6. A 4 would be 1 out of 6. I would get 4 out of 6 for that. And then the complement of that would be 1 minus 4 out of 6, which would be 2/6, which would equal 1/3. Now, let's logically make sense out of that. Odds and 4, if you put those together, what that leaves out is 2 and 6. Those are the only two dice rolls that we don't have for that. So 2 and 6 are 2 successes out of the possible 6. So what we've looked at is the probability working with independent events, which is associated with the word and we want to make sure that we understand what independent means, that the one does not influence the probability of the other. And when we do that, we take and we multiply the probabilities together. And then when we've got mutually exclusive events are, we use the word or with that, so it's one occurrence of trying to find probability, but you have more than one thing you're considering for success. If they're mutually exclusive, meaning there's no overlap, then we go ahead and add their probabilities. They're not mutually exclusive, we have to make sure we take into account that overlap in figuring our probability. And then the probability of the complement, where you just take 1 minus the probability of the event and you get the probability of the complement.